Good morning. Welcome to the next week of e-learning. This week we're going to be talking about related rates. This is definitely a weird semester where I guess we're going to spend the rest of the semester doing this. So anyway, thanks for listening to the video. Google Meet times have changed for this week, so you can look at the stream to check those out. Today we're going to go and look at our first section as far as applications goes. Usually I do this at the very end of the semester as a unit, but we're just going to do this as a single lesson and go from there. Do something new next week. So, related rates. You can read this slide. Essentially, we're going to set up some equations and use implicit differentiation using our time as our variable. We're relating rates of change, like how fast a side length is changing or how fast a volume is changing with respect to time. Okay, first example. And I might turn this into a couple of videos depending on how long it is. Well, I'll definitely turn it into at least 2 videos. A cube of ice is melting. The side is decreasing at a rate of 2 inches per minute. How fast is the volume decreasing when the edge of the cube is 3 inches? So here's some steps you could use for each problem. Number 1, identify with a variable what is known and what is to be found. So for example, on this one, I'm going to write it as a rate, ds dt. The side is decreasing at a rate of negative 2 inches per minute. So that's a known value. The rate at which the side is changing with respect to time, we represent that as ds dt. They want to know how fast is the volume decreasing. We don't know that. And the volume is going to be changing, the volume is going to be changing at a different rate depending on how big the shape is. Like it could be going faster or slower at the beginning than it is towards the end. So find the volume and the rate at which the volume is changing precisely at the moment when each side length is 3 inches. So I have ds dt, I have dv dt. I know I'm finding dv dt when the side length is 3. And then I need an equation relating the volume to the side. So volume equals side cubed. So now I'm going to take the derivative of both sides of the equation using the chain rule. The left side v dv dt, there's nothing there. V is just a function of time. But then s is an implicit function. So s is some function of time, but we don't see the t. So take the derivative of both sides with respect to time. The left-hand side derivative of v with respect to time is just dv dt. The derivative on the right is going to be 3 times s squared times ds dt, because it's an implicit function. Then I go back up. They gave me ds dt as negative 2. And they told me when s is equal to 3. So I can plug both those values in. And just multiply that out. And so when the side length of the cube is 3 inches, it's a big cube. When the side length of the cube is 3 inches, the volume is decreasing at 54 cubic inches a minute. So if the side length is 3, there's only 27 cubic inches of volume there, which means it would take less than a minute for that cube to completely melt. Back up to my steps, identified my variables, wrote an equation relating all the variables whose rates or change are given or trying to be found. I used the chain rule to differentiate each side with respect to time, and then substitute in the values. Okay, here we have a spherical balloon. Air is leaking out of it at 3 cubic inches per minute, so my balloon is getting smaller. When the radius is 5 inches, how fast is it decreasing? So as air leaks out of the balloon, the sphere is going to get smaller. At the point where the radius is 5 inches, how fast is it decreasing at that moment? So I usually start with an equation that I think relates everything. and then I go through and I see if I have everything covered. That's just my standard way of doing these. So volume of a cube is 4/3 pi r cubed. So my variables are v and r. So then the question is dv dt and dr dt. What do I have? What do I not have? So dv dt I have. The volume is decreasing 3 cubic inches per minute. Make sure you use your negative sign. And they want to know how fast is the radius decreasing. So what is dr dt? And specifically when r equals 5. So then I take the derivative of both sides of the equation with respect to time. The left-hand side is just dv dt. The right-hand side is 4/3 times pi times 3r squared, and then times the dr dt. So there's my chain rule with the implicit differentiation. And I'm going to plug in everything. We said r was 5. We said dv dt at that point was, or we said dv dt in general was -3. So the volume's going out at a constant rate, which is causing the radius to change. And the radius is going to change by different rates, even though the volume's changing at the same rate. So I work out the math all the way there, and I get about 0.01 inches per minute. For my third example, and I'm going to do the third and fourth example, and then pause the video, and then I'll do another video. Okay, so for example number 3, we have a cone. So I drew the cone, drew it upside down. A cone-shaped paper cup is being filled with water at a rate of 3 centimeters per second. The height of the cup is 10 centimeters. I didn't put that on the diagram, but that's my red line, 10 centimeters. The radius of the base of the cup is 5, so that's my green line. How fast is the water level rising when the level is 4 centimeters? So first I just start with volume of a cone. You might have to look up some formulas if you don't remember them. Volume of a cone is 1/3 times the area of the base of the cone times the height of the cone. So 1/3 pi r squared times h. They tell me that the volume is being filled up 3 cubic centimeters per second. That's how fast it's coming out of the water container. And what I need to realize in this problem is that the radius is changing, because if I'm going to use a pen here, or a blue marker. If I do the radius at this height, my radius is so big. If I do the radius at this height, my radius is bigger. If I do the radius down lower earlier in the process, my radius is smaller. It's getting closer to the full radius. So the radius is changing, as is the height. If I do that first one, the height's there. If I do kind of the middle one, the height's there. The bigger one, the height's there. So the radius and the height are both changing. So I have dv dt, they told me that. They told me the rate at which the volume is changing, and they asked for dh dt. So my problem here is that the radius is changing, but I don't have a dr dt. Going through a lot of work just to say that if I did implicit differentiation, I'd have a dv dt, I'd have a dr dt, and a dh dt, and I'd have to use the product rule. But I don't have dr dt. Like, they didn't ask me for it. They didn't give it to me. So what I really need to do is I need to come up with another equation that relates r and h. So this is specific to cones, but it could show up in other problems too. The idea is that we have an extra variable that's not a constant, and I need to write one in terms of the other. So let's see, if I put some numbers here, we said that 5 was the radius and that 10 was the height. And I'll use my blue lines again. But if I choose a different spot, then I have a different radius and a different height. And if you look at the blue triangle, so to speak, and the red-green triangle, those are similar triangles. So you can set up a proportion that looks like this. The radius over the height is equal to 5 over 10. Or you could set that up other ways, like the radius over 5. The radius over the big radius is equal to the small height over the big height. Radius over 5 equals h over 10. Doesn't matter with similar triangles how you set up that proportion. So the radius equals 1/2 the height. That's what we're going to see. Even if I said radius over 5 equals height over 10. Multiply both sides by 5 there, and I get radius equals 1/2 height. So now I can take my volume equation and plug in 1/2 h for the r. That allows me to rewrite my volume equation with just two variables, v, the volume, and h, the height. And that's great because those are the two rates that I have and want. I have the dv dt, the volume with respect to time, and I have the rate, or I want the rate of the height changing. So I take my new equation and I take the derivative of both sides with respect to time. So the left side becomes dv dt, the right side becomes pi over 12 times 3h squared times dh dt. Plug in the values that I have. Simplified 3 pi over 12 to pi over 4, plugged in 4 for h, plugged in 3 for dv dt, and worked it out from there. So I know this video is going on 12 minutes, but I want to show you the difference between example 3 and example 4. Example 4 is a cylinder instead of a cone. And the biggest difference here is that as the height changes, because I have this total height, but as this height changes, if I'm filling this up, I don't like that it's slanted. There we go. As that height changes, the radius is constant. So no matter where the water level is, or the wheat level is, the radius stays constant in this problem. So my volume formula for a cylinder is area of the base times the height, so pi r squared times h. I know that the radius is 10 as a constant. They told me the volume is being filled at a rate of 314 cubic feet per minute, and they want to know how fast is the depth of the wheat, so the height of the wheat increasing. So r is a constant, not a variable, so I just have two variables, v and h. Both of those rates are accounted for. Take the derivative of both sides of that equation. Remember that r is a constant, so pi r squared h, the derivative of that is just going to be pi r squared. R squared is 100, because r is 10, so pi r squared is really 100 pi times h. So chain rule though, because h is an implicit function, so there's a dh dt, and I can plug in my numbers and work that out. So that's the first video. I'll stop it there and then make